Should I start?
Yes, sir.
Hello everybody. Myself Dr. KG Sharma. So I'm going to present a lecture on VLSI issues and challenges. So if we talk about the interesting facts about VLSI, so about 30% of all the electronic components equipments consist of semiconductors, and about 20% of all ICs are ASICs. It means application specific integrated circuits. So in the year 2001, if we talk about up to that time, the world production of semiconductor components was for about $300 billion. So channel length, which was 0.13 micron in the year of 2000, 2000 reaches to 10 nanometer now. So what are the advantages of integrated circuits over discrete circuits? So if we talk about that, one is the cost. So because of the batch processing, the cost of the integrated circuit is degraded much below. So nowadays, if you talk about the cost of integrated circuit over the discrete components, so that cost is much below in case of ICs and comparison. Now, next point is reliability. So in discrete circuit, there are so many problems associated with, along with the loose connection, short circuits, and so many. But reliability in the case of ICs is much better. If we talk about the speed, so because the components are basically placed in the vicinity, they are close to each other, so the speed is also very much increased, as well as delays decreased. Next point is low power devices. In the same concept, because the components are placed close to each other, so because of that, the interconnect length is much less. So we are producing the low power devices. So after the advent of IC development in technology, more research started to embed more transistors in a single wafer, and then in 1970, microprocessors were developed, and microprocessors are nothing but a CPU of a computer. So if we classify the different ICs, the integrated circuits can be classified into ASICs, FPGAs, and silicon-on chips. So ASICs are basically application-specific integrated circuits, which are developed for some specific applications. Like suppose we are developing some robot, we are developing some toys, games, headphones, hearing aids. So for those purpose, ASICs were developed. It means it is not good to incorporate every time microprocessor or microcontroller for different applications, because that will add the cost and that will increase the complexity also. So for those purpose, ASICs were developed. FPGAs, field programmable gate arrays, are similar to digital signal processors. They are programmable. DSPs are reprogrammed and can be used for different processing and applications. But FPGAs are programmed for specific applications, and these are good for academic and industry, as well as university research applications. So in that, basically we develop the program in some front-end tool, and then we transport that program to FPGAs, and we can easily check the functionality in real-time environment. Next is silicon-on-chip. It means entire system is developed on a single computer, single chip. For example, input, output, memories, the DMA are developed in one chip. People may call it as a embedded system. So if we talk about VLSI system evolution, so in 1950s, the transistors were developed in Bell laboratories. 1960, integrated circuits came into the existence. Then in 1970s, the big revolution happened and microprocessors came into the existence. 1980, the digital signal processors were developed. You can imagine that these digital signal processors are basically the main component for the our mobile phones. Then 1990, FPGAs and ASICs came into the existence, and after 2000, system on chip were the main component. So if we talk about the brief history, the first computer was developed in 1832, and that was Babbage difference engine. It can execute some simple operations like addition, subtraction, multiplication, division in arbitrary sequences. And it operates in two cycles basically. One is a store and another is mill, which is nothing but execute. Included features like pipelining to make it faster, and complexity was around 25,000 parts. And it was costing around 17,470 pounds. In 1834, you can imagine, it was a very, very huge cost at that time. And then in 1946, the first electronic computer came into the existence, that is ENIAC. If we talk about the transistor age, the first point contact transistors was developed in 1947 by Bardeen and Breton. They produced one point contact transistor using two PN junctions. In 1951, Shockley developed a junction transistor which can be manufactured in quantity nowadays. Jack Kilby, who was working at Texas Instrument, invented a monolithic integrated circuit in 1959. He has constructed the flip-flop shown in the patent, as you can see in the figure, and that was basically the big revolution towards the integration of the different component in one single chip. In mid-1959, Noyce developed the first true IC using planar transistors. So back-to-back PN junction for isolation, diode isolated silicon resistors, and SiO2 insulation with the evaporated metal wiring on top. The big revolution happened in 1970. Intel started selling 1 kbit RAM of around 1103. Its density and cost make it the only game in town. In 1971, Ted Hoff at Intel designed the first microprocessor that is 4004, and that was having the 4-bit buses and a clock rate of 108 kilohertz. It has 2300 transistors and was built in 10 micrometer process. So if we just try to find out what happened in first 30 years after the advent of the first microprocessor, Intel 4004, in the year 1971, November 15, it was having the 4-bit ALU and operating at the frequency of 108 kilohertz. And it was having around 2300 transistors, and it was using 10 micron technology. After 30 years, Intel Pentium 4 came into the existence, which was developed in proposed in the market in August 27, 2001. And it was having the 32-bit architecture with the operating frequency of 1.4 kilohertz. 42 million transistors are used in that processor. Now, even you can think of it is much more than 55 million. So, and it was used using the 0.18 micron technology. Now, if you talk about, we are using the 10 nanometer technology. So these are the figures. So you can see the area which was involved to incorporate these microprocessor. So the Intel 4004 3x4 millimeter IC, and in this Intel Pentium 4 146 millimeter square IC. So if we talk about Moore's law, what he suggested in his initial age, that number of transistors per chip double in every 18 to 24 months. Initially, when he suggested this law, at that time, you can think of it was possible. It means, and the technology was capable to produce this kind of thing. It means the growth rate was matching with the prediction. But productivity or designing of larger design cannot be increased with the same pace of the transistor size shrinking. And now you can think of that era has come, that this Moore's law, it cannot be followed in present scenario. So the to incorporate more number of transistors in a single chip, we have to go for the scaling. It means we have to incorporate more and more number of transistors, so we have to decrease the size of the devices, size of the MOSFET. We have to incorporate the huge interconnections, and we have to shrink the size so that we can incorporate more and more functionality within the single chip. So motivation for scaling was that we can have more transistors per chip, and which is going to produce higher performance. And second point is less delay time, because the distance, or you can say overall structure, is shrinked. The delay between the two devices has decreased much below, and because of that you are achieving higher frequency too. So less VDD also, it means with the scaling we are also reducing the supply voltage, and because of that the power consumption is also reduced. It is basically the motivation, but actually the scenario is different. We cannot say that we are decreasing with the same pace, we are decreasing the supply voltage with the same thing, same pace, but obviously things are different. So scaling, if we talk about, so technology shrinks by 0.7 per generation. So with every generation we can integrate 2 times more functions per chip, and chip cost does not increase significantly. It means if you talk about the processor, within 6 months every processor, or within 1 year every processor is going to be obsolete, but cost of the processor is almost same. It is not going to be changed. So cost is almost same, but we are getting more and more functionality within the same chip. So cost of a function decreases sometimes by 2, but how to design chips with more and more function, that is the basic aim, basic goal of the scaling. Design engineering population does not double every 2 years in the present scenario, if we talk about. So basic thing is there, how we can achieve it, and this is the major task nowadays. So hence a need for more efficient design methods which exploit different levels of abstraction is the main scenario, you can say main motto of the engineers and the designers. Challenges for MOSFET scaling. So what are the challenges basically? So CMOS technology scaling has been a basic key for continuous progress in silicon-based semiconductor industry. Scaling is followed by Moore's law since few decades, which provided simple rules for transistor design to increase current density, circuit density, and the speed. Initially, it was good. Initially, we were in a same pace with the Moore's law. We are having double the size or double the number of transistors within 18 to 24 months. But after that, because of some complexity in the scaling pattern, we are now heading towards the different technologies, different transistor designs, and so on. However, as device scaling continues for the 21st century, doubled circuit density and increased performance followed by Moore's law cannot be maintained only by the conventional scaling theory. So what are the challenges in MOSFET scaling? Power supply and threshold voltage. This is the first thing that comes into the mind of design engineers, that as we are shrinking the size of the MOSFET, so MOSFET scaling tends to involve a reduction in supply voltage to keep electric field and the power dissipation within the limit. But threshold voltage cannot be scaled down, because threshold voltage is a physical parameter. So if threshold voltage is not scaled down, so the power dissipation will be more. Suppose if we take the simple example that we are scaling down the supply voltage from 2 volt to 1 volt, where threshold voltage is scaled down from 0.8 to 0.5. The difference of VDD minus VT is significantly decreasing, and because of this thing the leakage current is increasing, and because of that the power dissipation is also creating the difference. So but the threshold voltage cannot be scaled down too much, so when we operate in sub threshold region, then leakage current constitutes a significant portion of the total power dissipation. Next point is high electric field. The supply voltage cannot be reduced with the same pace of the channel length. So hence the scaling will increase the electric field strength. So you can just imagine that if suppose channel length is reduced, the distance between source and drain region is reduced, and if you are going to apply the voltage VDD, suppose VDS and VGS voltages, so what will happen? It means the electric field strength between the region will increase. So this may change the value of I off. So I off will change. I off means if you suppose you are basically trying to reduce the power dissipation, but electric field is increased, so it may be that at VT voltage you have applied, it means VGS or VDS is equal to VT, even though the things are not same. It means even though when you are thinking that device should turn off, it is actually not turned off. If also one more thing, that if high electric field is there, then in worst case the breakdown may occur. Another thing is gate oxide tunneling. So scaling of MOSFET requires appropriate reduction in gate oxide. So the thin oxide film subject to quantum mechanical tunneling give rise to the exponential increasing leakage current. So you can think of, if you are reducing the gate oxide thickness, so if you are applying lesser voltage, even though the same type of electric field will be generated, and because of that the things will not be as per our concern, as per our control. So further scaling can be realized by replacing the oxide gate with a high permittivity or high K gate dielectric. It means after 2000, basically what we have done, we have just shifted from the normal gate oxide to the high K gate oxide. Another thing is parasitic resistances and capacitances. So as the transistors are downscaled, influence of parasitic resistances and capacitances on current increases significantly. Next point is hot carrier effect. When carrier possess high energies having effective temperature gate and then lattice temperature, they are said to be hot. So main problem which arise due to hot carriers are parasitic gate currents, drain current degradation, decrease in transconductance, and shift of threshold voltage with time. So we can also, we have the technology, we can overcome this thing by using the graded drain profiles, and this is going in turn this is going to reduce the hot carrier effect. And next point is randomness of dopant distribution. As the size of the drain and source region is decreasing, because of that the doping is also becoming the critical issue. The doping is also becoming difficult because the instruments you require, that should be having a much high precision. So if doping is not proper, it's not uniform, then obviously the device will not behave in a desired manner. So as the device dimensions are reduced, it becomes difficult to place the dopant atom at exact and required position, and in turn that is going to reduce the control behavior of the device. Another is source to drain tunneling. If the MOSFET channel length between the source and drain becomes small enough, it can no longer be operated as a switch, because if source and drain region is much below, much less, so it will be difficult, because applying the same drain voltage is going to create much high electric field, and because of that, even the gate voltage is absent, the current will start conducting. So this is going to reduce the controllability of the switch. It means even though we are thinking that device should turn off, but still it is operating, it is generating some current. Next point is heat dissipation. So if heat dissipation is not proper inside the chip, hot spots are created on the circuit, which causes malfunctioning of the device. It means if suppose you have a chip, and in the chip there are the several devices, several sections of the devices, and some of the devices are dissipating much higher heat, and other parts are generating less heat. So what will happen, that those areas, when you are talking about the worst case, those areas will create the problem, and sometimes they may break down, and the whole of the chip, whole of the device will turn off. Next point is interconnect delay. It means as we are increasing the number of transistors per chip, as we are increasing the functionality of the chip, we have to interconnect all the devices. But since the distance is increasing, since the transistors, more number of transistors are there in a chip, so obviously interconnection of all the transistors is a big issue. So if you talk about the earlier Pentium processor, the initial Pentium processor, basically in that processor, we were requiring around 10 metal layers for the microprocessor, and around 8 to 9 metal layers for the interconnection of memories. Because memory, in case of memory, we may require less number of interconnections, or because repeatability is there, so we require lesser number of interconnection in that case. So interconnects are also playing a major role. It is, if suppose you are not able to connect the devices properly, then surely you have to go for the another metal layer, and that metal layer will create the problem, will increase the cost basically. So reduction in wire width increases the resistance, and hence increases the delay. This also reduces the speed. And the major problem nowadays is short channel effect, and which is going to produce the DIBL effect. It is going to reduce the subthreshold slope, and also it is going to produce shift in the threshold voltages. So technologically, if we talk about what are the practical difficulties, number one, people are running out of tricks for enhancing lithography. It means since transistor size is shrinking, it is much lower size. So creating different fabrication steps, these steps are also becoming very complex nowadays. Second point is complex designs are not limited by the number of devices, but they are basically limited by the wiring. Second point is, next point is high-end design may require, so as we talked about that, if we talk about the microprocessors, so those microprocessors design may require 12 metal layers to have the full interconnection of the different devices. So metal connection, metal may be taken as that the silicon surface is there, and over the silicon surface you are having the silicon dioxide, then you are placing the interconnection, then another metal layer, and so on. So that is also increasing the overall cost of the microprocessor or the devices, and because of that, considerable higher cost is there. Power is a major concern. If we talk about the scaling, we talk about that we are decreasing the size of the transistor, we are increasing more and more number of transistors in a chip, more functionality we are producing, more we are taking care of the scaling also. So we in general we have the assumption that the power is also going down, but in turn, if you just look towards this graph, as year wise, if you talk about, the power dissipation is also increasing. So we also should have some concern about this thing, that how we can dissipate this power so that device should not affect with that. In general, if you have seen the computer, there is the SMPS and there is some fan at the top of the microprocessor as well as some other places. So that is only there just to dissipate the heat. So if heat will not be dissipated properly and the heating components are not properly distributed over the chip, then surely the chip is going to be burned. So the MOSFET channel downscaling tends to involve proportional reduction in supply voltage to keep electric field and active power within limits. So power is a main problem. So not only the microprocessor you have to talk about, because nowadays there are so many electronic gadgets are there which are becoming popular, and one of them is the mobile phones. So mobile phone production is also increasing day by day, and in that mobile we always have the microprocessor as well as the DSPs. So these fabricating those microprocessors and the DSPs is also creating the major concern. So basic thing is there that not only microprocessor but other device design is also requiring concern towards the power dissipation. If we talk about the digital cellular market, if we talk about the how many phones are sold or shipped in units, so it has, if suppose we talk about 1996, 48 million phones were shipped, while in 2000, 435 million phones were shipped. So you can think of that requirement, as the requirement is increasing, the technology also has to adopt some new ways, some better ways, so that it can fulfill the demand. Another is interconnect restrictions. So while not directly related with the silicon technology, it means we are shrinking the size of the MOSFET, but it is not directly related with the size of the interconnect. It means not in the same pace, not in the same proportion, it is decreasing. So wires are also representing some fundamental problem of miniaturization of the circuit. So as transistor continues to shrink, wires and interconnect do not shrink at a similar pace. However, more and more wiring is needed to connect the increased number of transistors. Suppose if we are decreasing the size of the MOSFET, we are incorporating more number of transistors, we are also trying to reduce the width of the wires. So if wires width is decreased, then it is going to increase the resistance per unit length. So a smaller cross-sectional area means increasing resistance per unit length. Capacitance is also inversely increased. So overall, if we just talk about the RC time constant, that RC time constant is also increasing, and that is going to produce the delay in the interconnections. So as circuit speed increases, this lead to transmission delays limited by RC times rather than velocity of the electromagnetic waves. Problems with the current density. It means it is also related with the interconnect. So current density increases as cross-sectional area of the wire decreases. So current density is also limited by the electromigration, the movement of atoms by the electric field, and because of this region, there may be some open circuit failure or short circuit failure in the devices. Problem with longer wiring. If suppose we are using more number of layers to handle this problem of interconnection. So if suppose 12 layers of the interconnections are there, then it is also required that length of the wire is increasing. So if length of the wire is increasing, and because of the RC time constant, the delay is also increasing. So delays are not limited by the MOSFET. Delays are basically limited by the interconnections, and it is also going to lead to the higher production cost. So result is production limits are sometimes restricted by monetary barriers, not technological limitations. When we are fabricating the transistors on the wafer or on the chip, it is also required that the wafer surface should be flat. And as the technology is advancing, we require that the surface should be more flat, because we do not want any type of hillocks formation or any type of valley formation over the chip surface. So we have to look how much flat surface we are having. So if we talk about the 65 nanometer and below technology, the wafer planarity we have to achieve that should be 10 to 50 nanometer. You can imagine that if soccer field planarity, if we talk about that, that is up to this time, it is 5 to 25 micrometer we have achieved, but wafer planarity we have to achieve up to 10 to 15 nanometer, and that is adding also the cost in the different fabrication steps. Next is high leakage current. So there are basically 5 different major sources of leakage current. One is gate oxide tunneling leakage, another is subthreshold leakage, reverse bias junction leakage, gate induced drain leakage, gate current due to hot carrier injection. So now we are moving towards the another solution which is there with the MOSFET evolution. If we talk about the MOSFET, basically in MOSFET we are having source, drain, gate. If we talk about the planar MOSFET, so as we are shrinking the size of the MOSFET, as we are decreasing it, what is happening? Because of the size, because of the reduced channel length, we are having the short channel effect. In long channel MOSFET, there was no problem. It means if we plot the graph, we can say that the subthreshold leakage current or subthreshold slope, that slope is almost constant with the gate voltage and with the drain voltage. But when we are changing when we are switching towards the smaller dimension short channels, then what is happening? The barrier is reducing with the gate voltage, also with the drain voltage. So this is creating the problem. It means we are having in case of long channel MOSFET the subthreshold slope as well as I off, that is off current, that is also same. But in case of short channels, I off is changing. It means if we are changing the drain voltage, the current is increasing, suppose 100 times I off current and I on current. But again, if we talk about the short channel, the I off current may be increasing with the much better size, much better value. It may be more than 100 times. I on current will change with the same point, but I off current will change with the much better issue. So point is that how we can change the MOSFET design so that we can achieve more control over the electromagnetics. So after this planar configuration, we switched to the silicon-on-insulator design. So basic thing is there to avoid the leakage current from the source to drain, which is there within the bulk area, bulk region. So SOI is introduced. It means we have just decreased the bulk region, and because of that, the leakage current is decreased. So we switch to the silicon-on-insulator. Next is double gate MOSFET. If suppose we are controlling the channel current from one side, if suppose we can have the possibility to control the channel from other side also, then it will be producing good control over the electromagnetics. So if suppose we can have the gate from both of the sides, then obviously the controllability will increase and we will have the more control over the electromagnetics. So double gate MOSFET came into the existence to provide this kind of functionality, and one of the great advantage was the FinFET. So we basically created the fin over the surface, and gate is basically provided on both sides of the device. So when we are going to apply the gate voltage from both of the sides, then the channel current we can have more control on the channel current. So basically FinFET device, if you just look towards the fin structure, we are having gate from both sides. We are not having the gate from the top side. Top side is basically we are having the silicon nitride, and that is basically restricting the voltage to reach to the fin. So only two sides are covered by the gate voltage. But still, if we try to have the more control on the gate current, then we can have the top surface controlled by the gate. So if we can have the three sides, then we can have the better controllability. So Tri-Gate came into the existence. So Tri-Gates are basically the gates in which fin is covered from all the three sides, and whenever we are applying the voltage in the source and drain region, then obviously you can think of better controllability will be there. We can control the current in much better fashion. It means whenever gate voltage is present, then the current will flow. Whenever gate voltage is absent, the current voltage will not be there. Another possibility afterward was the pi gate. It means not only the three sides, but more area of the fin is covered by the gate, and this particular configuration you can think of is basically pie shaped fashion. So it is also if you just compare with the Tri-Gates, it is going to give you a much better control over the gate over the current. Again, if we just try to modify this design, we can move to the ohm gate, and in this more region of the fin is covered with the gate region, and more you can think of more better controllability can be achieved. And the best option till date is the gate all around. It means whole of the channel region is basically covered with the gate oxide material, and that gate oxide material is having it means gate oxide materials covering the whole channel. So better controllability, or you can say better control over the electromagnetics we can achieve in this. Any question पूछ सकते हैं क्या?
Yes sir, पूछ सकते हैं, but last में ले लीजिए क्वेश्चन सर,
क्योंकि अभी मेरा तो लगभग एंड है.
Any question to any of the nodal center? If they have any query, they can ask. Chaitanya College, Hyderabad. Sir, do you have any query?
Can I switch to the
Yes,
slide?
Chaitanya College.
Switch the slide.
No query, madam.
Okay, sir.
May I switch the slide?
Yes.
So basic thing is there that we had the conventional MOSFET, and our VLSI design is basically centered around this MOSFET design. We had the source drain region, we have some particular gate length, that is effective channel region, and this whole configuration, metal oxide semiconductor field effect transistor, is termed as MOSFET. So we all know about the MOSFET operation, that if suppose we have provided the voltage on the gate, then channel will be created, and when we are going to apply the drain to source voltage, then we will have the flow of electrons, or you can say the holes or charge carriers from source to drain region. So desired characteristics in this case is high on current and low off current. So we were basically talking about that in case of long channel MOSFET, we can achieve this thing properly. But what happened in case of short channels, basically we are having the high on current, but low off current is not becoming possible. So current between source to drain is controlled by the gate. N channel and P channel MOSFETs operate in a complementary manner. But good old MOSFET nearing limits, we are having the threshold voltage, we are having the subthreshold slope, swing, off current, and these all are sensitive to the effective gate length and doping variation. So because of this, we require the high design cost, we require high VDD, and hence we require high power usage. And finally, if we talk about the present scenario, it is very much painful to change the different configuration. So why new transistor structures we require? One is off-state leakage must be suppressed as the gate length is scaling down and allows for reduction in VTH and hence VDD. Leakage occurs in the region away from the channel surface, and we also need to get rid of this thing possibly. And gate length has not scaled proportionately with the device pitch 0.7x per generation in recent generations. So another option which was given was Silicon-On-Insulator. So by this way, basically off current, which was nothing but the leakage current, it was suppressed adequately by the thin body region. But due to leakage current through the region away from the gate, full depletion is not possible. So April 2011, Intel proposed, given some news, that world's first 3D Tri-Gate transistors on a production. New 22 nanometer transistor have an unprecedented combination of power savings and performance gains. So world's first demonstration of 22 nanometer microprocessor that was codenamed as Ivy Bridge, and that will be the first high volume chip used 3D Tri-Gate transistors. May 4, 2000, New York Times front page, New York Times news article was that Intel will use 3D FinFET for 2 nanometer technology and beyond. And that is the most radical change in the decade. There is competing SOI technology also, that is Silicon-On-Insulator. So TSMC, IBM, they are also giving some new transistors soon. Since 2001, ITRS shows FinFET and ultra thin body UTB SOI as the two successor MOSFETs. IBM 2009 produced produced 5 nanometer UTB SOI paper in 2009. So if we talk about the present scenario, basically we have the two competing technology. One is basically the FinFET or Tri-Gate technology, and another is ultra thin body Silicon-On-Insulator. So many foundries, we talk about the foundries, few foundries are basically working on the FinFET technology, Tri-Gate technology, and few foundries are basically still, they are stuck with the ultra thin body SOI, and they are still working on that to find out the ways how we can produce the much better transistors. So Tri-Gate achievement, basically, if we talk about in 2002, single fin transistor was demonstrated, while in 2003, multi-fin transistor was demonstrated. In 2006, Tri-Gate SRAM cells were developed and demonstrated, and 2007, Tri-Gate RMG process flow developed. So if you just talk about the Tri-Gates, basically internal research was there up to 2007, and after that Tri-Gate selected for 22 nanometer node, and then development and the manufacturing process started. So in 2011, basically you can you know that 2011 the Tri-Gate was developed in 22 nanometer technology. So bringing innovative technologies to HVM is the result of highly coordinated internal research development manufacturing pipeline. So 22 nanometer 3D Tri-Gate transistors, you can see that we are having a fin region, and you can see that the fin is basically starting from the silicon substrate. It means first of all we have the silicon wafer, then we are etching the other regions, keeping one region with the untouched and etching the region so that we can develop one fin region. And after that, oxide layer will be deposited, and then the gate material will be deposited. If we try to find out the difference between the FinFET and the Tri-Gate, basically in FinFET, the top surface is not used for the operation. Top surface will be covered by the silicon nitride. So and then gate material is deposited. So the gate voltage on the top is not affecting the channel current. Only the gate voltage which is there on the side walls, that is going to control the current. So 3D Tri-Gate transistors form conducting channels on three sides of a vertical fin structure, providing fully depleted operation. The transistor have now entered into the third dimension. What are the benefits of 3D Tri-Gate transistors? So dramatic performance gain at low operating voltage, better than bulk or partially depleted SOI or fully depleted SOI. So 37% performance increase is there at low voltage, and more than 50% power reduction at constant performance. Improved switching characteristic, it means on current versus off current ratio is also maintained constant, which was there in the long channel MOSFET, but it was not there in the short channel MOSFET, short channel planar MOSFET. Higher drive current for a given transistor footprint is there, only 2 to 3% cost adder versus 10% for FDSOI. So 3D Tri-Gate transistors are an important innovation needed to continue Moore's law, but still this is not an end. We are heading towards the gate all-around circuit. So these are the Intel products. In 45 nanometer process technology, we were having the Penryn and Nehalem processor. In 32 nanometer process technology, we had the Westmeyer and Sandy Bridge. And in 22 nanometer technology, we had Ivy Bridge Intel micro architecture processor. So cadence of innovation delivers new microprocessor efficiency on the 22 nanometer process. So what next? Future transistor path. It means now we are working on a silicon FinFET device with the width of the silicon equal to the channel length divided by 2, fin pitch around 3 times node, and gate pitch around 4 times per node. So now after that we are moving towards the silicon germanium FinFET, and that will be in 10 nanometer technology, and for 7 nanometer or 5 nanometer technology, we are moving towards the gate all-around circuit, vertical or horizontal feature, and it is going to provide you the improved electrostatics. So nanowire density challenge is also faced in this. And next is third, fifth FinFET technology, and that is going to provide the improved mobility, and basically it is following the IP structure. And next is vertical T-FET, and it is going to give you improved sub-threshold slope, and it is basically based on EP band engineering. Okay, you can ask any question.
Sir, आप बोल दीजिए सेंटर